Okay, so we have, in number 2, we've got a ring attached to 3 ropes. Just think of this as a 2-dimensional problem. 2 of the ropes are anchored. 2 of the ropes are anchored to the wall, and we have this 3rd rope for which we know the direction and the force. Now, the force that exists within a rope we call tension. You always assume that the direction of the tension vector, remember, if tension is a force, then tension is a vector, and that means it has a direction. That direction is always just parallel to the rope, which is fairly obvious. How could you have tension perpendicular, for instance, to the rope? And based on the fact that this ring is not moving, we're supposed to figure out what the tension is in ropes 1 and 2. So this is really a static equilibrium problem. As soon as you know something's not moving, that also means that it's not accelerating. Now, just because something's moving doesn't necessarily mean that it's accelerating. If it's moving in a straight line at constant speed, that would be constant velocity, and you would not need to worry about acceleration. But if it's not moving at all, if the velocity is 0, then that's a special case of constant velocity, which is 0 acceleration. Here is our ring with the 2 attached ropes, and then the 3rd rope with the known tension of 100 newtons. I'll call this T3. And then we have these unknown tensions parallel to the ropes. And since they called the ropes rope 1 and rope 2, we can call the tensions T1 and T2. And we are tasked with finding the magnitude of these 2 tensions. Now, since the acceleration is 0, since we know that that ring is in equilibrium, that implies that the net force on the ring is 0. So maybe the first thing you should establish when you start one of these problems is, what is the M in F equals ma? Because sometimes your mass is actually a collection of masses. Right now, we're talking about the mass of the ring. So if the ring is the mass in F equals ma, then we're really talking about the net force on the ring. This rope would be exerting a force on the wall. There's another force between this rope and this wall. We don't care about those forces. We care about the forces on the ring. And I see 3 of those forces. Maybe there's a gravitational force on the ring as well, but that was not described in the problem. We're not told what the mass of the ring is. And a small metal ring doesn't weigh very much anyway compared to the tensions in these ropes. So when you write this statement that the net force on something is 0, if it's a 2-dimensional problem, this is really a compact way of making 2 statements. One of them being that the sum of the forces in the x direction is 0, and then a simultaneous equation along the y-axis. So the first thing, I guess the second thing you should do after you decide which mass you're talking about is to choose a coordinate system. You need 2 perpendicular axes, which you can call the x and y axes. Pick the most convenient choice. I think it's fairly clear that our axes should be horizontal and vertical in this picture. So it's not always necessary to do this, but I'll go ahead and draw the x and y axes. And when I solve this problem, I'm going to be flexible with my trigonometry. I'm not going to worry about choosing the angles with respect to the x-axis. Remember those formulas, t cos theta, t sine theta, those will always work to give you the x and y components respectively if you measure the angle from the positive x-axis. I'm going to choose whatever triangle is most convenient here. Now, your book likes to emphasize that what you're really doing is taking the x components of the various vectors and summing them up. And I like that the book does that, at least in the beginning they do that. So what we're really doing is saying that T1 sub x plus T2 sub x plus T3 sub x equals 0. This is a bit overboard with the notation, so we won't always do this. But it does clearly show that what we're really doing is adding up the x components of 3 vectors. Each of these tensions is a force vector. That's why I wrote the letter for the vector with the vector symbol. We enclose, if you enclose the vector in parentheses and put the subscript x, it makes it extra clear that you're referring to the x component of a vector. Now, another way to write that would be just T1x plus T2x plus T3x is 0. That's perfectly valid as well. this means the x component of tension 1, the x component of tension 2. If you want to put those vector symbols, you probably need to put the parentheses. That's the notation used by your book, and I do like that. Okay, what can we conclude just by looking at this picture about those various x components? Well, T3, if we resolve it into components along the x and y axes, we can see immediately that tension 3 has a positive x component and a negative y component. See how the y component points down? So when we plop in T3 sub x, that will be a positive number. T1 clearly has a negative x component, and T2 has an x component of 0. Now, I could define an angle for each of these vectors and look at a triangle and use trigonometry to resolve the vector into components. But this one's so easy, there's really no need to do that. If your vector points parallel to the y-axis, it has no component along the x-axis because it's perpendicular to the x-axis. So you can just set that equal to 0. And if a vector is parallel to the x-axis, then the component of that vector is equal in magnitude to the length of the vector, right? Like we're going to find out what this number is, but let's say this is 5, that the length of this vector T1 is 5, then the x component is merely negative 5 and the y component is 0. Okay, so T1x would be negative T1. See what I've done there? T1 without the vector symbol means this is the length of the vector. Since the entire length is parallel to the x-axis, that is the x component with the minus sign. Because remember, if we just write the letter for a vector, we're talking about the length of the vector. That's a positive number. But I know that the x component is negative, so I have to insert the minus sign. And then I'll say plus 0 because T2 has no component along the x-axis. And then let's look at this triangle here. The hypotenuse is the 100 newtons. I would like the x component, which is the adjacent side. So I'll take T3 and multiply by the cosine of 30 degrees. That is the x component of T3. I do not need to add a minus sign because I know that the x component points along the positive x-axis. Set all those x components, or set their sum equal to 0, and now we can immediately solve for T1. I'll move T1 to the other side, flip the two sides, and T3 is 100 newtons. 100 newtons times the cosine of 30. You can use a calculator. I also like to try to remember the various trig ratios. The sine of 30 is 1 over 2. The cosine of 30 is root 3 over 2. But it's perfectly fine to just use a calculator for that. So I could plug that in, or I could just evaluate the cosine of 30, multiply by 100. And if I round, well, I'll call that 86.6 newtons. And that's a different number than I expected. Let me check that. Cosine of 30. Yeah, okay. Does it make sense? It's a positive number and it's fairly close to the 100. That kind of makes sense because this is a small angle. This component should be larger than this component. Okay, so we've already found T1. That's half the problem. Now we need to find T2. How do we get that? Well, let's go to the y equation. We'll say that the sum of the forces in the y direction must also be 0. And that means that T1 sub y plus T2 sub y plus T3 sub y has to equal 0. Find all the y components, add them up, that must be 0. What is the y component of vector T1? That one's easy. Vector T1 is orthogonal to the y-axis, so the y component of T1 is 0. 0 plus, this one is also easy. Because the vector is parallel to the y-axis, we don't need to project out any component. We don't need to multiply by cosine of an angle or sine of an angle. The y component is the full T2. And I don't need a minus sign because it's pointing along the positive y-axis. What about T3 now? Well, we know that the y component of T3 points down, so it does need a minus sign. It's the side opposite the angle. So I will say minus T3 sine 30 degrees, and that's got to equal 0. What are we solving for here? T2. So T2 would be 100 newtons again times, and this one again I have memorized, sine of 30 is 1/2. So T2 is 50 newtons. And those are the two answers that we were asked for, or the two numbers. Let's check the solutions manual. Yeah, everything looks good. Number 7, I said in a previous video that we don't talk about electricity in this class. That's largely true, but in this particular problem, they happen to have made up a scenario where there's a plastic ball hanging from a string and somebody has, let's say, rubbed an acrylic rod with a piece of rabbit fur, which tends to charge it electrically. Have you ever taken a balloon, rubbed it on your hair, and noticed that it makes your hair stand up? So it's easy to give something some static charge. And we don't need to worry about the nature of this electric force or how to calculate it. They just give it to us. We're told that the rod exerts a horizontal electric force, which makes the ball swing outward on the string until it's in equilibrium at that angle. And we need to find two things. How strong is that electric force? And what's the tension in the string? So this is another static equilibrium problem. Static because the ball is not moving. It's just at rest. Equilibrium because it's not accelerating. Here's my ball on a string. This is L for length. We're told that the length of the string is 60 centimeters. We may or may not need that. The angle that the string makes with the vertical is 20, and I've exaggerated that angle just to make the picture easier to look at. So the idea is, let's say this is the rod that you rubbed against the rabbit fur, and you bring it nearby, and I'm not even going to bother drawing it, but there's an electrical repulsion that causes this thing to swing outwards. Now, what prevents it from swinging even further? Like if there really is an electric force pushing to the left on this mass, and let me draw that force. I'll put the tail of the vector on the object itself, and I'll call this F sub E for electric force. Why doesn't this ball just continue to move to the left? How come it stops? Well, that would be the tension in the string. The tension is applied to the ball in this direction, parallel to the string. And if we look at the components of that tension vector, there's a component that opposes the electric force. So technically, I should draw these with the same length because I know that the mass is in equilibrium. So the horizontal component of the tension balances the electric force. Now, do you see that if this is 20 degrees or theta, this is also 20 degrees theta? There's a couple ways to see that. If I draw the vertical here, alternate interior angles, it tells us that because these are parallel lines, if this is theta, and then for the same reason, this is theta. So there's a couple ways to see that. And what's the force that we're missing? Because notice that the string is also pulling up on the ball. If that were the only vertical force on the ball, wouldn't the ball start to accelerate upwards? So there's got to be something pulling down on the ball. And of course, that's gravity. So I could put the gravitational force in here as well. F, gravity. And because they gave us the mass, we could calculate that. And I just realized I have yet to go over this. So real quick. Let's say here's a diving board and a pool. If some kid jumps off the diving board, so here they are, about to do a belly flop into the pool. Let's forget about air drag. If the only force on this person is gravity, and I will probably present this very important idea in its own separate video. Here's the gravitational force. No other force is on this person. And we know that they're going to be accelerating. They have a downward acceleration of 9.8 meters per second. That's an experimentally determined number. You guys have already measured that yourselves. You did it in the lab using Tracker. So if this person has a mass m, we can say the sum of the forces along the y-axis must equal their mass times their acceleration. And we can choose a coordinate system, the typical one. X is horizontal, Y is positive in the upward direction. The only force that I see on this person is this vertical force of gravity, and I put a minus sign in front. Fg is the magnitude. The Y component of that force needs a minus sign because it points down. Notice it has no component along the x-axis. And we know observationally that this thing will accelerate in the negative direction at a rate of 9.8 meters per second, which we abbreviate as G. G is our letter that means 9.8 meters per second. So the minus signs cancel, and we get this observation, this very simple observation. The gravitational force on a piece of mass near the Earth's surface is numerically equal to the quantity of mass in kilograms times 9.8 meters per second. And let's look at the units here. Force comes out in newtons. Mass is in kilograms. And that means that the units of G must be newtons per kilogram so that the kilograms cancel and the units match. We've been thinking about G as 9.8 meters per second, but it's the same thing as 9.8 newtons per kilogram, which is roughly 10 newtons per kilogram. What does that tell you? Here on the surface of the Earth, every kilogram of mass weighs about 10 newtons. So for example, if you have a mass of 80 kilograms, that's a pretty typical mass for an adult human being. That's kind of redundant. I guess an adult is a human being. So if your mass is 80 kilograms, the force of gravity on your body would be 80 kilograms times, I'm going to round 9.8. Well, I'll write 9.8 newtons for every kilogram. That's roughly 10. 10 times 80 is about 800 newtons. So a typical adult has a weight in newtons of something like 800 newtons. In the US, we like to measure our weight in pounds. Maybe that's something like 200 pounds, 150 pounds. The number comes out bigger in newtons. And that's roughly 1,000, very roughly 1,000, which is, you could write that as 1 kilonewton. So I think it's worth remembering that the weight of a larger human being is about 1 kilonewton. That's 1,000 newtons. That's worth remembering because it helps you, it's a good standard when you're talking about larger forces like the thrust of a rocket, for instance. Okay, so you can always calculate the gravitational force on an object by taking its mass and multiplying by the strength of the local gravity field. You have to memorize that. F equals mg. Weight, I shouldn't say weight because our book has a slightly different definition of weight, but gravitational force is mg. Where does that come from? It merely comes from Newton's second law for the special case of free fall acceleration, where you know that the only force is gravity. That's it. That's all it is. All we've done is write Newton's second law for the special case of free fall acceleration, and we come to this conclusion. So now that we know that, sorry about the detour there, we can continue with this problem. And let's turn this picture into a free body diagram. I believe this is the first time we're talking about free body diagrams. Honestly, I don't like the name. Free body usually means something that has no force acting on it. And very often we're drawing free body diagrams for particles that have many forces acting on them. So I don't really like the name, but you don't need to draw the ball, just draw a dot. You could even go with an X. I'll use a dot. So this dot represents the mass in question. And you draw all of the forces that you can find on that particle, and you make sure to put the tails of the vector or the vectors on the particle itself. So I've kind of already done it here, but a free body diagram is one that's uncluttered by a sketch. So here's my tension vector. Let me make this bigger. We've got the electric force and then gravity. And this time I'm trying to make the vectors have the appropriate length. That's not really crucial. I'm not going to take up points on an exam because you didn't draw your vectors with the appropriate length. So that's not very important. And here's where I can resolve into components now. So this is the tension T, this is the electric force, this is the gravitational force, which we know to be mass times G. And we're supposed to find a couple things. What's the tension in the string? What is the electric force? Now, you don't always have to know where you're headed when you start a problem. Honestly, sometimes the best way to proceed is to draw your free body diagram. That's what this is. And then write F equals ma. We know that the ball is in equilibrium. So we can start by saying that the total force in the x direction is 0. Remember, this is short for the net force in the x direction. And what have we got? Well, remember, let's be careful with the angle. The angle that they gave us is up here. Typically, the x component is something like t cos theta. That's if you were measuring theta from the x-axis. But in my picture, I labeled this angle as theta. The x component here, because I'm using, I guess I should specify, I'm putting my x-axis in this direction and my y-axis in this direction. My x component for t would be this component. That's really the side opposite theta. So I would say t sine theta. That would give me the x component. Notice I've skipped the step where I say, I guess I could write it here. So F sub x equals 0 means that T sub x plus electric force sub x plus gravity force sub x is 0. The sum of all the x components are 0. I'm jumping straight into actually evaluating these various quantities. T sine theta is this component of the tension. Now the electric force points along the x-axis. So I don't need to multiply by cosine or sine of any angle. I just say minus electric force because it does point along the negative x-axis. And the component of gravity along the x-axis is 0 because of my choice of axes. So I don't even have to worry about that one. And since those have to sum to 0, sorry, that says equals 0, I can immediately solve for the electric force in terms of the tension. Electric force equals T sine theta. Now, unfortunately, I can't finish this problem yet because, or this part of the problem. I do know the angle, so I could calculate the sine of the angle, but I don't actually know the tension. These are the two quantities we're being asked for. And I've got one equation with both of those two unknowns. You cannot solve a single equation for two unknowns. So we're kind of stuck at this point. Maybe we can use this in a moment. Now we go to the y-axis. The sum of the y forces must also equal 0. If we look at the picture here, this force has no component along the y-axis, so I don't even need to worry about it. This component of the tension is positive because it points up, and you'll notice it's the side adjacent to my defined angle of 20 degrees. So I would actually use the cosine function, and I would say t cos theta with the positive sign minus, since gravity is along the y-axis, I don't need to worry about multiplying by the sine or cosine of any angle. I just say minus mg has to equal 0. And this is great because we know everything in this equation except for t, which is one of the quantities we're being asked for. So this says that t is equal to mg over cos theta. And I could now plug in numbers for, I could plug in the mass. We're told that the mass is 1 gram. Now, 1 gram is 1,000th of a kilogram. Remember, the kilogram is actually the SI, the standard unit of mass. But oftentimes, dealing with grams is more convenient because a kilogram is kind of heavy. So a gram is 1,000th of a kilogram, which is why I like to call it a millikilogram. Millikilogram. That's the same thing as 1 gram. Totally redundant. Nobody else says that. So I'm just being humorous here, or attempting to be humorous. A millikilogram. So I could plug in numbers right now, 20 degrees, 9.8, 1,000th of a kilogram. But I'm not going to do that because here's a technique that's going to serve us well later in the semester. This was valid, but I'm going to cross that out so it doesn't distract you and write instead t cos theta equals mg. Yes. So I'll call this equation 2. And then the first equation that I wrote up here, I'll call it equation 1. I'm just going to flip the two sides and say t sine theta equals F electric. And then check this out. equation 2 divided by equation 1, which is not something that I remember doing in high school algebra, but it's a perfectly valid technique. We can divide the left sides by each other, divide the right sides by each other, and set them equal to each other, to one another. So that would be, oh, you know what? I actually want to do equation 1 over equation 2. Yeah. Equation 1 divided by equation 2. That would be t sine theta over t cos theta equals Fe over mg. See what I did there? I took this and divided it by that. And then I took this and divided it by that. And I set them equal to each other, which is a valid algebraic technique. If you don't, or if you're skeptical, try to convince yourself of that. But this is a technique that we'll use repeatedly this semester. And you'll notice that the t's cancel, and sine over cosine can be rewritten as the tangent, right? So the tangent of theta is electric force over mg, and that means electric force is mg tangent theta. This is one way to solve for the magnitude of the electric force in newtons. Your solutions manual does it a little different. They just solve this equation directly for tension first, and then they go back and plug that value into this equation. Either way, I'm showing you this technique because we're going to use it a lot later in the semester. So now it's time to plug in numbers. We've got 1,000th of a kilogram times 9.8 newtons per kilogram times the tangent of 20 degrees times the calculator. 20 tangent, and I find this is times 10 to the negative third. So I can write this as 0.00357. I'm rounding. That's a very modest force. Not surprising because static electricity forces in everyday life tend to be pretty small. Now that we've got that number, can we go back? Your solutions manual rounded this to a 6 there. Can we go back and solve for the tension? Yeah, we could just use this equation directly, but rather than deal with that pesky 0.001, let me use this equation. Tension would be electric force divided by the sine of the angle. So if I take that, it's still in my calculator. This is the electric force magnitude, and I divide it by the sine of 20 degrees. I get 0.01 newtons. All right, either way. When it comes to the algebra, there's no necessarily one way to do it. But to rehash here, first we decided what's the m in F equals ma. We drew a sketch. We chose our axes. We turned that sketch into a cleaner free body diagram. Once the FBD has been drawn, your next step would be to write or to apply the condition for equilibrium, which is that the sum of the forces in the x and y directions are 0. Once you've written those equations, use a little bit of trigonometry to get the various components. After that, it's just a math problem. It's just, in this case, it was solving 2 equations for 2 unknowns. Those 2 unknowns were the electric force and the tension. And that overall procedure, you will see again and again. It's just the, it's what most of these problems amount to for the next 3 chapters. Write F equals ma, draw your, or after you've drawn your picture and your free body diagram, evaluate the various components of the forces, and then it's a math problem. It's an algebra problem at that point. Next up is number 15 from chapter 6. We have a very massive spaceship. In a moment, I'll show you how to think of this number in terms of the metric ton. And its thrusters provide a force of 1,200 kilonewtons. Remember, 1 kilonewton is roughly the weight of a large human being. So that's a very large force, over a force greater than the weight of 1,000 people. I guess you would need a force that large to accelerate something this massive. So we're told that it fires the thrusters for 20 seconds. Now, during those 20 seconds, there's a net force on the spaceship, and that means we know the spaceship will accelerate. If it's a constant acceleration, we can use our constant acceleration kinematics to figure out how fast it's going at the end of those 20 seconds. Then we're told that it coasts, which means it moves at constant speed for 12 kilometers, and we're supposed to figure out how long it takes to go that distance. So this is really the simultaneous application of Newton's second law and constant acceleration kinematics. Here's my super lame spaceship. We will talk about this more later in the semester, but when a spaceship ejects fuel backwards, it pushes on the fuel backwards. The fuel must push forward on the spaceship. So the thrust force is in that direction. I'll just call it F sub T, and we'll label the mass of this thing. It's almost unnecessary to do this because it's a one-dimensional problem, but I suppose we could assign a coordinate system like this and say the sum of the forces in the x direction is the mass of the spaceship times the acceleration of the spaceship. Now, there is a subtlety here. The mass of the spaceship, which we're given, we're told that it's, I need some more space here, 8 times 10 to the 4th, I believe it was. 8.0 times 10 to the 4th kilograms. That's 10 to the 4th. I'm going to use one of those zeros over here. So I'll turn the 8 into 80. That would be 80,000 kilograms now. And I like to write it that way because 1,000 kilograms is a metric ton. 1 metric ton is the mass of 1,000, or is a mass of 1,000 kilograms. And the thrust force, that was 1,200 kilonewtons, so times 10 to the 3rd newtons. Now, if I've called to the right, the positive direction, then the only force I see is the thrust force, and it gets the plus sign. And now I can solve for the acceleration. So the subtlety I was about to allude to is the fact that the mass of the spaceship is always decreasing if the thrusters are on. As long as the spaceship is burning and ejecting fuel, its own mass is decreasing. And you would need to take that into account to really analyze the motion. That gets a little more complicated. You actually need calculus. I don't think it's really covered in your chapter, or it may be presented as a special topic, the so-called rocket equation. So I guess the assumption we're making here is the rate at which it's burning fuel means that the change in mass is insignificant compared to the initial mass of the spaceship. So now we can plug in our numbers here. 1,200 times 1,000 newtons divided by the 80,000 kilograms. And we're talking about acceleration right now. Should it surprise you that my units come out newtons per kilogram? Well, I just talked about the fact that G, the free fall acceleration, can also be interpreted as the weight per kilogram on the surface of the Earth. So newtons per kilogram, meters per second, it's the same thing. Remember, 1 Newton, just think F equals MA. A Newton is a kilogram meter per second squared. So of course, a Newton per kilogram is a meter per second squared. What does this number come out to be? We don't expect it to be very large. Yes, it's an enormous force, but it's also an enormous mass that we're accelerating. See how the 10 to the 3rds cancel? I didn't plan that, just worked out that way. 15. Okay, so more than 1 G of acceleration. Now that we know the acceleration, let me assign some times. T0, that'll be 0 seconds. That's when the thrusters turn on. T1 is 20 seconds later, we're told. That will be when the thrusters turn off. Now, once the thrusters turn off, there's no more force on the spaceship. It will just continue at the speed it already had in the same direction. That's Newton's first law, right? The law of inertia. T2 is the unknown time at which the ship has coasted. Whoops. Was it 12 kilometers here? Number 7. No, this is number 15. How far did we coast? 12 kilometers since time T1. So we're not counting the distance it may have traveled or did travel while it was accelerating. And so what we're being asked to find here is the time between T1 and T2. How much time has passed between turning off the thrusters and coasting those additional 12 kilometers? find delta t, which for this problem will be t2 minus t1. Okay, well, let's first find how fast we're going at the end of these 20 seconds, because then we can plug that constant velocity into our next equation. So the velocity at time 1 will be the velocity at time 0 plus the acceleration between those two times t1 minus t0. I am using the constant acceleration kinematic equation for how velocity depends on time. This is really delta v equals a times delta t. How do I know that the acceleration is constant? Well, we already calculated it. If the force is constant and the mass is constant, so is the acceleration. We could have, in here, we could have just plugged in F over m and done this all in one shot, but it's kind of nice to know what the acceleration is rather than plug everything in all at once. So the initial velocity is 0, we started from rest. We're picking up speed at 15 meters per second, and the time interval here is 20 seconds. 2 times 15 is 30, so we're going 300, whoa, meters per second, which is something like 800 miles per hour. That's pretty darn fast, which means it's not going to take long to travel those additional 12 kilometers now that the spaceship is going this fast. So now we can go straight to the displacement equation for constant acceleration. Delta x is v initial times delta t. Remember this one? V initial delta t plus 1/2 a delta t squared. Well, during the second phase of the motion, the thrusters have turned off, so the acceleration is 0, and my initial velocity is actually, that would be v, that's the speed that we just calculated, right? v1 is the velocity at the end of the acceleration phase, those 20 seconds, which is the same as the acceleration at the beginning of the next phase. So I will say delta t is delta x over v initial, which is velocity 1. And we know that that additional displacement is 12 kilometers. So 12 times 10 to the third meters divided by 300 meters per second. So at a speed of 300 meters per second, how long will it take to go 12 kilometers? It'll take 40 seconds. Okay. Newton's laws coupled with constant acceleration kinematics. You will see many more problems like that. Number 18 from your homework seems like a rather trivial problem. It looks innocent enough, but there's a surprising amount of depth to this problem if you're interested in thinking about it. In fact, the crux of this problem was at the heart of Einstein's exploration of gravity, his reformulation of how gravity works, and gravity as curvature of space-time. May have began with considering problems like this one. So we're told about an elevator in a skyscraper and how long it takes to get up to speed. So we can use these numbers to find the acceleration of the elevator. And then we're told that there's a person of typical mass standing on the elevator or in the elevator. And we're asked to find the passenger's weight for 3 different scenarios. Now you may be thinking, well, why would their weight change just because they're in an elevator? The gravitational force shouldn't change. Or maybe you're thinking, okay, as the elevator goes higher, they're farther from the center of the earth where the gravity gets weaker. That's really not what this problem is about. Yes, the G field does get weaker as you rise to the top of a skyscraper, but it's a minuscule difference. This is much more about how your perceived weight changes. We all know what it's like, I think, to be in an elevator that begins picking up speed in the upward direction. You feel a little heavier just for a moment when the elevator begins to accelerate. And at the top, let's say you take a fast elevator up to the 20th floor. When the elevator slows down at the last second, you might feel a little lighter for a moment. That's what this question's about. So weight is really going to be the normal force on your feet. It's how hard the ground pushes on you. That's what your weight is. So we're supposed to find the weight before the elevator starts moving, while it's accelerating, picking up speed, and then once it reaches its cruising speed. Just when you thought the drawings couldn't get any worse, here's my elevator. Here's a person inside with really strange body dimensions standing on a scale. And this thing could be accelerating up or down. Remember the rule about velocity and acceleration If this elevator is moving up and speeding up, then the acceleration would need to also point up. If you're speeding up, V and A point in the same direction. If the elevator is slowing down, V and A would have to point opposite, so the acceleration would point the opposite way. And if you're not speeding up or slowing down, that means you're not accelerating, and this acceleration would just be 0. So what are the forces on this person? Well, if they're near the surface of the Earth, we can't forget about gravity, the pull of the Earth's gravitational field, but the scale is pushing on the person. After all, if you're accelerating upwards, gravity is not going to accomplish that acceleration. If gravity were the only force on you, you would be in free fall and accelerating downwards. Well, you could be rising and slowing down if you had been launched upwards, but you certainly wouldn't be accelerating upwards due to gravity alone. So there obviously has to be an outside force contributing to the acceleration beyond gravity. The only force you can recognize here or identify would be the normal force. That's the scale pushing up on the person. And we call that force N for normal force. This is really your weight. So if you weigh 150 pounds, that means if you just stand on a scale in your bathroom and your house is not accelerating, the scale has to push on your feet with 150 pounds to prevent you from falling. But if you took that same scale and put it on an elevator, as the elevator is picking up speed upwards, your body would actually be pressed harder into the scale. In other words, the normal force would go up, and the weight that registers on the scale is that force. So maybe the scale says 180 pounds during the moment that you're picking up speed. That is your weight. It's that force between your feet and the scale. And that force, in some sense, gets transmitted throughout your body. You feel heavier. I don't know anything about the biology there, but you've got nerves within your body that detect those internal pressures. So you sense the increase in your heaviness, your weight. Okay, this is a straight up application of F equals ma. I've called up the positive direction. Sum of the forces is mass times acceleration. Remember, the mass of this person is 60 kilograms. Because I called up positive, N gets a plus sign. And gravity gets a minus sign, so that's minus mg. We've seen now that to calculate the gravitational force, we just multiply the person's mass by their free fall acceleration. And that's got to equal mass times acceleration. And since this is a one-dimensional problem, I'm just going to dispose of the subscript. We'll just call it the acceleration a. Now we can solve for n. N is equal to mg plus ma. And hopefully you've got enough experience with algebra that you have a compulsion right now to factor out the m, factor out the mass. And here's the result we wanted. Your weight for any possible acceleration is calculated from your mass, the local acceleration, or the local g field strength, and your instantaneous acceleration. So how heavy you feel as you stand on that scale will change as your acceleration increases or decreases. And there's another way of thinking about this. Let's define some fictional g field, which I'll call g prime, as g plus a. That's the 9.8 that you're standing in on Earth's surface plus your additional acceleration. Then you can write this result as n equals m g prime. And this looks a lot just like the regular result, right? If what's your weight just standing on the Earth's surface, you're not in an elevator, it would just be mg. So your weight, it's almost like you're on another planet where the gravity field is stronger. Let's take an easy example. The 9.8, let's round it to 10. What if your acceleration was 5? 10 plus 5 is 15. So your acceleration would be 50% of the free fall acceleration. And when you go to calculate your weight, you would find that it's 50% greater than it normally is. No pun intended with the word normal there. So by being in an elevator that's picking up speed at half a g, in other words, 5 meters per second, you feel just as heavy as you would on a planet with a g field strength of 15 meters per second, which is kind of a profound thought, right? That being in an accelerated elevator feels like being on a planet with stronger gravity. And Einstein really thought deeply about this and came to the radical conclusion that not only would you feel heavier, not only would the scale register a greater force, he suggested that all physics within the elevator would look the same, whether you were actually in a gravitational field that was stronger or just in an elevator picking up speed on planet Earth. He suggested that there's nothing you could do, no experiment you could perform within this elevator that would tell you the difference. Because if the elevator has no windows, and this is kind of silly, but let's say you were drugged and kidnapped. I know that's too dramatic. I don't know, aliens abducted you and you were unconscious, asleep for days, and you wake up, you have no idea where you are. All you know is you appear to be standing on 2 feet in a box and you feel heavier than you normally do. But your body doesn't look any different. So it's not like they stuffed you full of pizzas. Einstein suggested that nothing you could do within the confines of that elevator box would tell you whether you were actually on a planet where the gravity's stronger, and that could account for why you feel heavier, or you're just in an elevator that's picking up speed. It doesn't matter if you throw a baseball within the elevator and watch the trajectory that it takes. You could do experiments with electricity and magnets. That wouldn't help you. Lasers, nothing would clue you into the difference. So again, very profound thought. And that led him, that was probably the thrust behind arriving at his new theory of gravity. But we don't need to talk about all that stuff just to solve this problem. Let's take this result now and solve parts A, B, and C. So when you're at rest, before the elevator starts to accelerate, well, then your acceleration is 0, and you would just plug in 0 for A, and of course you get mg. Kind of an obvious result, right? If you're in the elevator and it's not accelerating, you just feel your normal weight. Once it's accelerating, and do we know the acceleration? We would need to be given that in problem 18. First we need to find A. Well, that's change in velocity over change in time. We're told that this elevator gets up to a speed of 10 meters per second from 0 to 10 in 4 seconds. 4 goes into 8 2.5 times, I think. Or excuse me, goes into 10. So a modest acceleration. That says 2.5 right there. Now that we know the acceleration, we can plug it into our equation. N is m times g plus a, which would be, I would like to do this in symbols actually. This is roughly mass times g plus, isn't this a quarter of g? If g is 10, 2.5 is 1/4 of that. So this is about 1/4 g. So we can write that as 1.25 g. G plus 0.25 g is 1.25 g. So rather than actually plugging in, I mean, of course we could plug in the mass of 60 kilograms and 9.8 and find that the person now feels like they weigh 735 as opposed to their usual 588. But those numbers are actually less illuminating than the ratio here. So if they're accelerating at 1/4 of g or 25% of g, then they will feel 25% heavier, right? 1 times mg is 100% of your normal weight. 1.25 is 25% greater. That's a nicer way to think about it. Now for part C, also trivial. Once the elevator has reached its cruising speed, it's no longer accelerating. Then when you plug 0 in again for A, you just get the same result as part A. That shouldn't surprise you. Remember the discussion about absolute reference frames? You may think that when you're sitting in a chair in your room on planet Earth, you're not moving, like you're at rest, as opposed to the people flying over your apartment in an airplane. You know, they're moving according to you. And the moon is moving around you because the moon orbits the Earth. But don't forget, you're on a planet that's actually flying through space at 30 kilometers per second. That's 20 miles every second. And it's doing that all year, every year, your whole life. Hopefully, because if it doesn't, that's bad news. So, you know, where can you go where you're actually not moving? You could try going to the sun, but remember the sun is also moving around the center of the galaxy. So it's really more about acceleration. It's the whole business of inertial frames. Whether you're sitting on the surface of the Earth at rest, that's pretty close to an inertial frame, or you're moving straight up at constant speed in an elevator, that's also close to being an inertial frame. In both of those situations, your weight would just be mass times the strength of the G field with zero acceleration. Number 22, another very massive rocket with a very large thrust force. And you can compare these numbers to actual rockets if you want. I may do that later. You can pull up the Saturn V data on Wikipedia. I think that was one of the largest rockets ever built back in the Apollo era, or the rockets being built today by SpaceX and some other companies. No air drag, that'll simplify things. Given those parameters, what is the rocket's initial upward acceleration for part A? Okay, getting slightly better with the drawing here. Remember, if a rocket is ejecting fuel downwards, the rocket gets pushed upwards. So the thrust force is up. It's 3 times 10 to the 5th. Well, that's the same as, I'm going to use 2 of those zeros. 2 of the 5 zeros can turn this into a 300. And then if you subtract 2 from 5, you get 10 to the 3rd, which is a kilonewton. So 300 kilonewtons. I chose to write it that way because it allows you to conceptualize it. This thrust force is equivalent to the weight of 300 large people. All right, and we know what the mass is originally. They say initial mass because, again, as you burn fuel, the mass of the rocket is actually decreasing. What is the initial acceleration? Well, let's call this the positive y direction, and we will apply Newton's major dynamical result, that's F equals ma, along the y-axis. It's really easy to forget about gravity here, to just say, okay, thrust force equals ma. How come I didn't worry about gravity in the previous rocket problem? The way that the problem was phrased, I think we were to assume that the rocket was far out in space, away from any gravitational field. Here, we're trying to lift off vertically from Earth, so we have to account for gravity. Okay, we've got the thrust force in the positive direction, gravity in the minus direction, or it's in the negative direction, hence the minus sign, equals ma. Here's what I'm going to do. Divide both sides of the equation by m and solve for the acceleration. So that's thrust force minus mg over m. And it would be perfectly fine to plug in numbers here, but here's a nice way to think about it. Let's distribute the m. Notice here the m's cancel. So the acceleration is the acceleration that you would have if you were not in a gravitational field. That's like the previous rocket problem. If you just took, I'm sorry, this is supposed to say Ft for thrust force. If you just divide the mass into the thrust force, that would be the acceleration absent gravity, absent air drag, any other forces. But because we're in a gravitational field, we have to take that acceleration and subtract the free fall acceleration. Now, you don't want to use that thought process to solve an exam problem, for instance. I need to see that you're properly applying Newton's second law. That's what this class is all about. But it is nice to keep that in mind and have some intuition about the physics here. So 20,000 kilograms divided into 300 kilonewtons. 300 kilonewtons divided by 20 metric tons. And actually, we could have done that in our heads, right? Because of the powers of 3. This is 300,000 divided by 20,000. So it makes sense that it's 15. There's that number again, 15 meters per second minus the 9.8. So roughly 5 meters per second left over. So if it weren't for gravity, this rocket would be picking up speed at 15 meters per second squared, but it has to overcome gravity. Now, as it climbs away from the Earth, this term will actually decrease. The gravity gets weaker, and so the acceleration would increase a little bit. But we're not supposed to worry about that in this problem. Most of the semester, we're not concerned with the fact that as you rise from the Earth's surface, that the value of g actually decreases a bit. There's another reason in this problem why the acceleration changes. So we're told in part B, let's go back to the problem here. In part B, we're told that once the rocket reaches 5 kilometers in altitude, that's like 3 miles, so way up there, now the acceleration has actually increased from 5 to 6 meters per second. So it's picking up speed at a greater rate. Why would it do that? Well, it's not about the thrust having increased. I think a lot of rockets, the way they're designed, the thrust is independent of how much fuel is left. And don't quote me on that, but so if it's got the same thrust, but it's picking up speed at a greater rate, and we're supposed to ignore the fact that the gravity has gotten weaker up there, then it must be because the rocket is now lighter. It has less mass. Same force, less mass equals greater acceleration. So this time we're solving for a different variable. Part A, we were solving for the acceleration. Now we know the acceleration and we're supposed to find how much of the fuel was burned. Well, we can still start from the same place, F equals ma. That's usually your starting point with these problems, after all. And it's still thrust up, gravity down. But the unknown that we're now solving for is the mass. So let me put mg on the other side and factor out m. And that means the mass at, I'll call it m1. This is the new mass when we're at this altitude of 5,000 meters. Notice we don't actually need the altitude, right? That's not a number we have to plug into an equation. And your book will often do that, give you some extraneous information. So we just take the thrust force and into that we divide g plus the acceleration. We still have the 300,000 newtons, but now we've got 9.8 plus not 5 anymore, but 6 meters per second. Okay, so this is newtons, and I could write this as newtons per kilogram. And you see how the units that come out are kilograms. So I'm going to go 9.8 plus 6. I hit equals, and I've got this reciprocal button on my calculator. Then I multiply by 300,000, and I find that the new mass is 18,987 kilograms, which is roughly 19,000 kilograms. Remember, we started with 20 metric tons of fuel. So delta M, the change in mass, is about 1 metric ton. That's the amount of fuel that's burned. That's probably reasonable. Those rocket ships, spaceships, they burn through insane amounts of fuel. Remember, most of the energy from all that fuel is being used to lift the rest of the fuel. So it's a very inefficient way to get things into space at the appropriate speed. The solution of this next problem, number 23, requires Newton's universal law of gravity, which I have not talked about a whole lot yet. So I will be posting a separate video about that law and how intuitive it really is. But I will be using it in order to solve this problem right now. So we're told how far the Earth is from the sun. We know the Earth's mass, we know the sun's mass, and we're supposed to figure out the Earth's acceleration towards the sun. Earth's acceleration towards the sun. What is that? What are we talking about here? Is the Earth falling towards the sun? Well, if this is the sun, and of course this is not to scale, we know that planet Earth is making a giant orbit around the sun once a year. And just by virtue of moving in a circle, we know that there is an acceleration that points towards the center. That's the centripetal acceleration. It's not 9.8. Why should it be 9.8? 9.8 is how fast things fall to the Earth if they're already close to the Earth's surface. Why would the Earth necessarily accelerate towards the sun at 9.8 meters per second? We're going to find that it's a very different acceleration. Now, why does it accelerate? Well, F equals ma tells us that whatever the direction of the acceleration is, the force on your mass must be in the same direction. So if this is the direction of Earth's acceleration as it orbits the sun, then it must also be the direction of the force on the Earth. What is the nature of this force? What do we call that force? Well, it's gravity. The same force that makes apples fall off of trees to the ground also makes the planets orbit the sun. And we have an equation, a very simple formula that will allow us to calculate that force of attraction, the gravitational attraction. Now, here's a very profound thought. It's a simple thought or simple idea. If you could somehow stop the Earth in its tracks, Maybe like in Blazing Saddles, if you put up a toll booth in the middle of space where you had to put in a couple dimes, somebody's going to have to go back and get a bunch of dimes, and the Earth had to just stop in its tracks. What would the Earth do? Well, since its lateral motion would be removed, then instead of falling around the sun, so to speak, it would begin to fall straight towards the sun. And we're going to calculate that rate. Fortunately, it takes an awful lot of force to stop the Earth in its tracks. And we don't expect that to happen anytime soon, maybe ever. It would take like a planetary collision to cause something like that. Okay, well, if we've been talking about things falling towards the Earth, here's an object in free fall. Let's call this mass M, and it's accelerating towards the Earth. We say sum of the forces equals mass times acceleration. That's Newton's second law applied to this object in free fall. And we give the acceleration a special label. We call it G, and we know that it's 9.8 on Earth. And since the only force acting is gravity, we can call it Fg. So this is our first way of calculating the gravitational force of planet Earth on an object falling towards the Earth. It's just Newton's second law with that special label for the acceleration. And it would really work on another planet as well. You could take your rock, let's say, to the moon and plug in a different free fall acceleration. I think it's 1.6 on the moon, and calculate a different gravitational force. So as long as you know what this acceleration is, because you've measured it using Tracker or some other experiment, then you just multiply the free fall acceleration by the mass of your falling object, and that would tell you the force on that object on that planet. But there's another way to calculate this force. There's another formula for doing that, and here's what it is. If I refer to the massive object as big M, let's say this is the mass of Saturn or whatever, and this is your little object falling towards the planet, little m, Newton's law of gravity says that the force of attraction between those two, because it's actually a mutual attraction, they really pull on each other with equal and opposite forces. It's proportional to the product of the masses. So if you make the falling rock bigger or you make the planet more massive, the force of attraction between them would go up. And then you divide by the square of the distance between them. So in this case, R would be the distance between your falling rock and the center. You go from center to center. So it's clear that as the distance increases, the force would go down. And we're talking about planet Earth, which is very far from the center of the sun. And we don't expect this number to come out very big, even though the sun, because if we take the same law of attraction and apply it to the Earth and the sun, we have an incredibly large number for the sun's mass and a very large number for the Earth's mass as well. But we're dividing by an even bigger number. The square of the distance is a very large number. And so this, the force between them will come out pretty darn small. Now there's something I've left out here. If you'd like your force to come out in newtons, and you're plugging in your mass in kilograms, and your distance in meters, you need a constant of proportionality out front. And that constant of proportionality is a very small number, which has been measured. Let's just round this, this 6.67. If you round that up to 10, I'm being really sloppy. 10 times 10 to the negative 11th is like 10 to the negative 10th. And the units there aren't important, but you can see it would have to be Newton meters squared per kilogram squared so that everything works out, so that the dimensionality works out. So it's an extraordinarily small number out front, which tells us that gravitational forces are only significant for enormous masses. If you were to calculate the force of gravity between just two little chunks of rock out in space, 1 kilogram, 1 kilogram, when you take 1 times 1 over 1 squared, you know, if they're 1 meter apart, and then you multiply by this tiny number, you get a very tiny force. Gravitational forces only become significant when you're talking about extraordinarily large masses. So now that we have the force law for the gravitational attraction, we can, let's set up a coordinate system here. All I really need is one axis. I'll call this the positive direction. So my axis points in that direction, and towards the sun for this problem will be positive. And I'm referring to Earth. So I'll say that the sum of the forces on Earth is the mass of the Earth times the acceleration of the Earth. I'm applying F equals ma to planet Earth. And the force that I see is the force of attraction between them, which we now know to be big G, mass of the sun, mass of the Earth, over the square of the distance between them. That's Newton's universal law of gravity times mass of the Earth times the acceleration. And we see that the mass of the Earth is on both sides, so we can divide that from the equation. And now we've got an expression for the acceleration. It's big G times the mass of the sun over the square of the distance between the center of the sun and the center of the Earth. Now think about it. We've just found a formula for the free fall acceleration towards the sun out at this distance, the distance from Earth to the sun. But because the mass of the Earth canceled, it really doesn't matter whether we were calculating the free or the acceleration of Earth towards the sun or some floating piece of space junk. Maybe there's, I don't know, a satellite that escaped from the Earth that's now orbiting the sun at the same distance. You could apply the same reasoning that we used here to this satellite and find that its acceleration towards the sun is going to be the same number. So it's like the value of G in a way. It's kind of like G for the sun out at this distance. This is the free fall acceleration towards the sun when you're really far away from the sun. That's a lot like 9.8, but 9.8 tells you the free fall acceleration towards the Earth when you're already at the Earth's surface or very close to it. But it's the same thing. It's the acceleration in a gravitational field. Okay, so let's plug in numbers here. And do we expect it to be 9.8? You know, if you took a tennis ball way out here at the same distance that we are from the sun, but far from the Earth, and you dropped it, would you expect it to fall towards the sun and pick up speed at 9.8 meters per second every second? Let's find out. 6.67 times 10 to the negative 11th. And the mass of the sun was given as 1.99. I believe it's times 10 to the 30th. I should really have that memorized. We're looking at number 23 here. Yes, 10 to the 30th, which is insane. Of course, that number is gradually decreasing, right? Isn't the sun getting less massive as it burns through its fuel every day? And we divide by the square of the distance between them. Now, I happen to know that the distance between the Earth and the sun is 150 million kilometers. I have that number memorized because it shows up so much. 150 million kilometers. In SI units, that would be 150 billion meters, because every kilometer is 1,000 meters. It's really easy to forget that conversion factor. Okay, let's put all this into the calculadora here. Times 1.99 times 10 to the 30th, divided by 150 billion squared equals, okay, I get 5.9 times 10 to the negative third meter per second squared. Sorry, that's 10 to the negative third right there. Much lower than 9.8. There's a nicer way to write this. 10 to the negative third meters. Isn't that a thousandth of a meter? We have a name for a thousandth of a meter. We call that a millimeter. Let's round this to 6. This is about 6 millimeters per second. And that has a nice interpretation. Yes, Earth's acceleration around the sun is a centripetal acceleration, but if you could stop the Earth in its tracks with the toll booth and just wait and watch, you would find that the Earth begins to fall towards the sun, and every second, the Earth would speed up by 6 millimeters per second. So after falling for 1 second, Earth would be moving towards the sun at only 6 millimeters per second. Now, Einstein would say that at our distance from the sun, the curvature of space-time due to the sun's presence is very weak, and that's why the acceleration is so low. But as you get closer and closer to the sun, that acceleration would begin to grow tremendously, and at some point it's going to be way bigger than 6 millimeters per second. So the Earth on its crash course towards the sun would begin to pick up speed at a greater rate. But way out here, the curvature of space-time is very gradual. You may have seen some graphics with a bowling ball supported by like a rubber sheet, and there's that big dip around the bowling ball. That's what we're talking about here. Number 29, truck parked on a slope. Well, that truck better have its handbrake on to prevent the truck from rolling down. We're supposed to find the magnitude of the friction force. And then they do this misleading thing. They give you the coefficient of friction because they're hoping that you screw up and just assume that static friction is mu times the normal force. If you've watched the video that I posted about the 3 different categories of friction forces, you'll remember that you would only multiply the coefficient of static friction by the normal force if you knew that you were dealing with the max possible static friction force. In general, static friction is whatever it needs to be. So we will use the condition for equilibrium, F equals ma, where acceleration is 0, in order to find the actual static friction force. Here's a truck on a ramp, and I think we're told that this is 15 degrees. The truck's mass was what, 4,000 kilograms? I believe it was. What's the size of the friction force? Okay. Well, in a previous problem, I suggested that the first thing you should do is choose your mass. I think it's fairly obvious that since the truck is the thing not accelerating, then the truck's mass is the m in F equals ma. So this is the mass that we're talking about. I will sketch all the forces I can identify. Don't forget about gravity. Gravity is going to pull down on the truck with the mass mg. The ramp is going to be pushing normally to the surface. There's the force that we call the normal force. And there's also static friction. Now, if the truck has a tendency to slide down the ramp, then static friction would have to point up the ramp. F sub s. Notice I am not writing F sub s max. Now, what's the most natural choice of coordinate system for this problem? This is the force we're interested in, F sub s. And it would be pesky to have to resolve F sub s into an x and y component if we chose our axes that way. So why don't we just make the natural choice and say that up the ramp is the positive x-axis and normal to the ramp is the positive y-axis. Do we actually need the normal force? Well, if we were going to use this equation, max static friction is mu times n, then yes, we would need to determine the normal force. And that would require going to the y-axis to find n. I will do that, but we don't actually need to do that for this problem. Because if we look at the x-axis, you've hopefully had plenty of practice with this by now. If you resolve the gravity force into components parallel to and perpendicular to the ramp, see how I've made a right triangle where the full gravity vector is the hypotenuse? Remember, this is also theta. If this is 15 degrees, this is also 15 degrees. We can calculate this component of gravity because we know that this is 15 degrees and we know the mass of the truck. And I don't see any other forces in the x direction. All we've got is static friction and mg. So we say the acceleration being 0, that's the condition for equilibrium. The truck is not accelerating. That means that the net force on it must also be 0. Specifically, the net force in the x direction must be 0. And that means static friction with the plus sign minus mg sine theta. This is the component opposite theta. Those have to sum to 0. So the static friction only has to balance the component of the truck's weight, or the, I'll say weight, the component of the truck's weight, which is actually parallel to the ramp. That's it. So we take the 4,000 kilograms, each weighing 9.8 newtons, times the sine of 15. And I find that the static friction force must be 10,146 newtons. Now it is worth asking, is that possible? Because if this ramp were steep enough, you can imagine that the truck would just start to slide. Once this angle gets close to 90, I just can't imagine any tire technology or handbrake, whatever, I don't know what's inside a truck, that would allow it to not slide. So let's just check that it's even possible to get this much static friction. Let's figure out what the max static friction force is. Remember, they told us that the coefficient was 0.9. You know, asphalt and rubber, that combination of materials has a pretty high static friction coefficient. So as a check, we'll go to the y-axis now to find out what the normal force is. We say sum of the forces in the y direction must also be 0 because the truck is in equilibrium. Normal force gets a plus sign, and then the adjacent component of the gravity force gets a minus sign. Minus mg cos theta has to equal 0. Great. So the max possible static friction force would be mu times the normal force, and we see that the normal force is mg cos theta. Let's plug in numbers. I'll do it from right to left. Cosine of theta would be the cosine of 15 degrees times 9.8 times the 4,000 kilograms times 0.9 for the coefficient. And believe it or not, we could actually develop over 34,000 newtons of friction between the tires and the road. Notice there's no mention of how many wheels there are. It doesn't seem to matter. That seems a little strange, right? Because you might be thinking, well, if you have more wheels, there's more contact, more surface area of contact between the tires and the road. It seems like you should be able to get more friction. That's true, but the more tires you have, actually that's not true. The more tires you have, the less of the weight is supported on each tire. So the normal force on each tire would actually go down. This is a subtlety here that the book probably doesn't talk about. It's not like we're applying this relationship to each tire individually. We're just regarding the entire truck as one object with one point of contact. But it works. It actually works out that way. And I didn't expect to be talking about this, but is there a simple explanation for why the normal force or the friction force doesn't depend on how much surface area of contact there is? Because again, you might expect that with more tires, you'd have more contact with the road, there should be more friction. Well, think about it this way. Remember that graphic with the two surfaces with all the bumps on them? The harder they're pushed together, the more difficult it is to overcome the interlocking between all those bumps and the valleys, and then the bonds between the particles. Well, the more tires you have, the more contact with the road you have, the less weight is on each tire, meaning each tire would be compressed less into the road. So everything kind of cancels out. It's like, yes, you get more surface area, but you get less normal force per surface area. In the end, it doesn't even matter how much surface area you have. Now, is that totally true? Is that 100% accurate? Again, this is a very simple model for static friction that works pretty well. If you wanted to do a more accurate calculation of friction, perhaps you would have to take those other things into account, like how much surface area there is between the tires and the road. Last one for this video, a 50 metric ton locomotive, I love that old word for train, is traveling at a modest 10 meters per second, that's like 22 miles per hour, when the engine and the brakes fail. Oh no. How far will the train roll before it comes to a stop? Well, Newton's first law says that unless there's a force acting on something, it'll just keep going. Straight line, constant speed. So supposing the train tracks are straight, why would this train track come to a stop to begin with? Well, the real answer would definitely include air drag. Trains are somewhat aerodynamic, I think, but they're basically boxes. As they plow through the air, they're going to be slowed down by the drag from the air. But the problem doesn't mention that. And even if it did, the problem doesn't give us the dimensions of the train cars. It doesn't tell us the size of the front face of a train car, which we would need to know if we were going to calculate air drag. And that is something that you do in chapter 6. So I think we're supposed to assume, or I know we're supposed to assume, that there's no air drag. We don't worry about that at all. Okay, so if there's no air drag, then why is this train stopping? Because they tell us that the track is level. It's not going uphill. It's not gravity that's causing the train to slow down. Well, we touched on this in the introductory video about the 3 types of friction. a train track has metal wheels, or excuse me, a train has metal wheels. Maybe they're steel. I don't actually know. I think we're supposed to assume they're steel. Steel wheels on steel train tracks, which means we're talking about rolling friction. Remember, you would only use static friction for a vehicle if you're talking about a vehicle that's speeding up or slowing down. If you're just cruising, and when I say speeding up or slowing down, I'm talking about under the action of the engine or your brakes. If you're braking or speeding up with the engine, then static friction comes into play. But if you're just trying to coast, just cruise at constant speed, then the friction that you would use is rolling friction. So I've got these numbers memorized here, and let's turn to the diagram. Well, this is our first chapter where we apply Newton's laws. So there's got to be a normal force on the train. Yes, the normal force, or there are normal forces on all the wheels, but remember, we don't worry about that. Just model it as a single normal force. Why is that normal force there? It's to support the weight of the train. Now, if the train is rolling forward in this direction, then rolling friction will always oppose that motion. If you had a force of rolling friction in the same direction you were moving, wouldn't that help you out? That would make the train actually speed up. That's silly. So we know that the rolling friction points that way, F sub R. I don't really need to draw a free body diagram for this problem because it's not like we've got vectors that we have to resolve into components. There's really no need for a free body diagram. I can see clearly what's going on in the horizontal and vertical directions. Okay, for the coordinate system, let's do this. Forward is the positive X axis, up is the positive Y axis. And can I start by saying zero acceleration means zero force? No, this is not a static equilibrium problem. We know that the train is slowing down by assumption. So the train is not in equilibrium. We have to start with F equals ma. This is the special case of F equals ma, where you know that the acceleration is zero. Okay, let's start with the y-axis, and you'll see why. Some of the forces in the y direction are mass times acceleration in the y direction. Well, there's no reason this train should be accelerating vertically. That would be weird, right? If it was lifting off the train tracks. So we can't assume that quantity is zero. And that means that the train is in equilibrium as far as the y-axis is concerned. So normal force with the plus sign minus gravity has got to equal zero. And we've just concluded really that the normal force on the train is equal to the weight of the train. That's a little confusing because in the problem with the elevator, remember, we decided that weight is the normal force. So this word weight gets used to mean different things at different times. Right now, by weight, I mean the gravitational force on the train. In this case, it really is equal to the normal force. We're going to need that because of this model for friction. Remember, rolling friction is coefficient of friction times normal force. The harder the train is pressed into the tracks, the greater the rolling friction on the train. And now we know what the normal force is. That's why I chose to do the y-axis first. Okay. So now we can say that the rolling friction force is mu times the normal force, which is mg. Great. We'll save that for later, as in right now. Some of the forces in the x direction is mass times acceleration in the x direction. I can't cross out the acceleration now because we actually expect that the train is slowing down. Okay, well, what's the only force that you see along the x-axis? To the right is positive, friction points to the left. So I give it a minus sign, negative rolling friction, because remember, FR is just the magnitude of the rolling friction force. Now we take this expression for rolling friction. It's mu times the normal force. We got the normal force from there, and we plug that in here. So negative mu mg equals ma. And I'm glad we did it this way, where I carried the symbols all the way through to the end, because now I can see that the mass of the train evidently doesn't matter. There's no need to plug in that number. The acceleration is merely negative mu g, which is a very clean result. We already know that g has units of meters per second. So the The rate of acceleration is just this multiple of the free fall acceleration. Why the minus sign? Well, the train's moving forward, and we know that the acceleration is backwards because the train is slowing down. And here's where you have to use your brain a little bit. Well, this whole thing, I suppose, requires that, but the problem didn't tell you what the coefficient of friction was. You're supposed to just know, I guess, that it's steel on steel, which you can look up in that table, 0.002. 0.002. That's the whole idea behind rail being so efficient, right? So that's a very modest acceleration. 0.0196 with the minus sign. And that's not really the end of the problem, is it? What are we actually being asked to find? Let's go back to the statement of the problem here. How far will the locomotive roll before it comes to a stop? How far? That sounds like a displacement to me. That sounds like a delta x. So we're looking for a delta x. We know the initial speed when it starts slowing down. That's when the brakes fail and the engine fails. We also know the final speed, because if it comes to a stop, then its final speed is 0. So we've got delta x, we've got v's, and we know the acceleration. Notice there's no mention of time there. We don't know the time. They're not asking for the time. That should clue you in that maybe we should use what I call the v-squared equation. So for constant acceleration, which is what this is, it's just a number. We can say this: v final squared minus v initial squared equals 2 times acceleration times displacement. This is the constant acceleration kinematic equation, or one of them. And we're solving for this. Okay, well, final velocity is 0. So negative v initial squared over 2 times a, and now we just plug in numbers. We started at 10 meters per second, square that. We're slowing down at negative 0.0196. And you can check that the units work out the way they should. We get a meters upstairs. 100 divided by 2 is 50. So 50 divided by, the minus signs cancel. Whoa, 2,551 meters, basically 2.6 kilometers. This train is going to roll really far. So it doesn't keep going in a straight line at constant speed forever, but according to the law of inertia, I guess it's not surprising that this train, which is very massive, right? It's got lots of inertia. It maintains its velocity for quite a while. No, the force is not 0. The friction force is not 0, but it's also kind of insignificant, which is why it takes a while to really change the train's motion. Let's actually calculate the friction force. The coefficient of 0.002 times, what was the mass of the train? I didn't write that down, 50,000. Okay, 980, basically 1,000 newtons. The weight of one person. Ha! The weight of one person. Yeah, I mean, if you could somehow stay in front of a train like you're on a skateboard maybe, and you're just pushing on it, pushing backwards on the train with a force equal to your own weight, I don't think you'd slow that train down by much. It's going to take a long time to bring it to a stop. And there it is.